we talked about our substituent groups. Suffix changes from ane to il, right? The YL ending. So we go from methane to methyl if it's a substituent group. We can also have other substituent groups and functional groups on alkanes as well. So the next group, you can also have halogens as substituents, and these are the same naming convention as the halogens as ligands for inorganic compounds, right? So the IDE or INE endings for these go to O. And then we label the group the same way we did before, and then we still do the carbon number followed by a dash and then the halogen in this case. So for example, if we had something like 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, something like this, and let's say we had a chlorine here, what would the name of the parent chain for this molecule be? Yep, the parent name we have, let's count, we have 1, 2, 3, 4, 5, 6, 7, right? There's no double bonds or anything in there, so this becomes heptane, right? Heptane, hept is our prefix for 7 carbons. And then on the 4th carbon, we have what? Yeah, we have chloro. We have chlorine bonded to the 4th carbon, so this becomes 4-chloroheptane. And the same rules for the other substituent groups apply. If we have multiple of the same halogen, we separate those by a comma. If we have halogens or different halogens at different spots, those are listed in alphabetical order, and then numbers and letters are separated by dashes, and then numbers and other numbers by commas, right? So if we had 1, 2, 3, 4, something like this, and we have BRF, right? We're gonna try and put these on the smallest possible numbers as well. That rule still applies. What would the name of this compound be? Yep. 2-bromo, right? Bromine becomes bromo. Then we have another dash. -3, because on the 3rd carbon, we have a fluorine, and fluorine becomes fluoro. And what's the name of the parent chain here? Pentane. Right, 2-bromo because we have on the 2nd carbon 4, 5. We put the bromo first because it comes in alphabetical order. We number it this way because it puts our substituent groups on the smallest possible number. And then we separate our 2 substituent groups, 1 fluorine and 1 bromine, by a dash indicating where both of those, the number being the number on the parent chain where both of those substituent groups are located. All right, so that's how we treat if we have a halogen on our alkane. All right, any questions on that? So the same rules for halogens on alkanes. You just treat them like an alkyl group. The only thing that changes about the name is it goes from chlorine to chloro. All right, so these, we're naming the structure when we're given it. Usually naming the structure is a little bit easier. Going the other way, starting from the name and generating the structure, sometimes people have a harder time doing. Okay, so see if you guys can draw 3-ethylpentane. This is our parent or main chain, and that's 5 carbons, so it's gonna be 1, 2, 3, 4, 5. right? And then 3-ethyl says on the third carbon we have how many carbons attached to it as a substituent group? What does the prefix eth mean? 2, right? So this is 2 carbons. So on the third carbon, 1, 2, 3, we have 2 carbons attached to that. So we have an ethyl group there.
So what direction does it matter?
If you go up or down, generally because the kink is going down, you go down. Otherwise, it gets really hard if you have a lot of functional groups there. So generally, you go in that way. Since you guys are just learning this and only learning it within a week, like I'm not going to be that strict about that. If you're going in different directions, you know, depending on who you take for for organic chemistry, they'll be more picky about the drawing. If it's not legible, they might not give you credit for it. But so you see in the student store, a lot of people, they get the stencils for drawing organic chemistry molecules. It helps make the molecules look neater. So this is be 3-ethyl pentane. Any questions on that one? And so if that wasn't enough, for each of these alkyl substituent groups, you can also have structural isomers of those substituent groups. So what that means is you can have isomers of alkyl groups. And so I'm going to introduce a notation here just to make things simpler. If you ever see R, that represents the parent, bless you, parent or main chain, right? So if I have an ethyl group, and it can be drawn like this. What that means is that these 2 carbons here, where's my highlighter, are bonded to some parent chain, but it's any arbitrary parent chain. I don't want to draw pentane every time. It can be butane, propane, all of those. So this just represents that 2 carbons are bonded to a parent chain, right? So this is 2 carbons bonded to a parent chain. It's also worth noting right now that whenever you're bonding to a heteroatom, meaning not carbon or not hydrogen, or even hydrogen, this edge right here doesn't represent another carbon atom. When you have it drawn to something like an R group, or it can be an oxygen, or maybe a nitrogen, right? That's saying that this carbon is bonded to this R group, right? There's no extra carbon here, right? So sometimes it's useful when we're looking at penmanship if I would probably draw this a little bit closer, because we're saying that this is bonded to that R, right? It's not a third carbon that's in between the 2. It's bonded to that group. So if we were to look at something like this is what a ketone is, it's a double bonded carbon to an oxygen. Those 2 lines going up, even though they're not touching the O, they're bonded to that O. This is saying that this carbon is bonded to this oxygen. So this looks like that in the Lewis structure, right? So that's important to note, right? That way we're not counting extra carbons. It's a common mistake I see, is that people count 3 carbons bonded to this R group because they think this edge of a line is a carbon. No, this carbon is bonded to this R group here, right? And R just represents any parent chain. And the reason I do that is because when we're talking about substituent groups, that can be on a cyclohexane, it can be on a regular hexane, heptane, it can be on anything, right? So it just means that there's an arbitrary parent chain that this is attached to. And so the purpose of why I'm introducing this is because once we get to substituent groups that have 3 or more carbons, now you can have different isomers of that chain, which means that we can have, and not just isomers, but structural isomers, meaning they have different connectivity. Because if we look at something like propyl, So that's the first example we'll look at. We'll look at propyl. Right, propyl has how many carbons in it? 3. Prop is the prefix for 3, right? So propyl, we have 3 carbons, right? So we have an R group, and it has 1, 2, 3 carbons bonded to it, right? Is there any other way you think I could draw this that doesn't violate the octet rule for any carbon without including any double bonds or triple bonds? 3 carbons attached to this R group. This is a propyl group. All right, so these are the 3 carbons on the propyl group. If we have another one coming out here, we can have this is an isomer of the propyl group. Right? If you counted all the hydrogens and all of the carbons in this, you would see that we still have 1, 2, 3 carbons, right? That kink in the line represents a carbon. On the left-hand side, there's 3 hydrogens bonded to that carbon, 3 here. The central carbon there, the central dot, has how many carbons it's bonded to? Or how many? It has 1 bond here, 1 bond there, and 1 bond there. So 3 bonds are accounted for. So how many hydrogens are there? 1, right? Because we need to have 4 bonds to every carbon. So there's 1 there. So this, how many total hydrogens here? 7. The other propyl group on the left here, we have how many hydrogens bonded to this carbon? 2, right? Because there's 1 bond here, 1 bond there, which means that there needs to be 2 hydrogens there. So this has 2, this one has 2, and how many does the last one have? 3, because at the terminal edges, you always have 3 hydrogens if there's no double or triple bonds, right? So there's 3. So that has 7 hydrogens as well. And both of them have 7 hydrogens and 3 carbons. So they're isomers of each other. They're the same chemical formula, but the connectivity looks very different from each other, right? That looks like a peace sign, and that one looks like a branch. So these are called isomers of each other, and when their substituent group is an isomer of another, that you have a different name, just to make things more complicated. So this isn't propyl, this is, isopropyl. Propyl. So this is isopropyl. It's easy to remember, isomer of propyl. So this is the only isomer propane or propyl that you can have, right? Any other modifications, you have to either remove hydrogens, add double bonds, and then you're changing the chemical formula. So we're only going to go up to butyl, but you can imagine the more carbons in the substituent group, the more possible isomers you have. So with butyl, you'll have 1, 2, how many carbons are in butyl? Pentyl would be 5. It'll be 4, right? We'll have 4 carbons. So we have 1, 2, 3, 4 for a regular butyl group. And this is usually called N-butyl. Then we have 1, 2, 3. This one is called isobutyl. Right? All I've done, and you notice that it's an easy way to draw isomers of organic compounds without changing the number, keeping the chemical formula the same, but the connectivity different, is all I did is I took this little last carbon here and I slid it down here, right? When I slide that down, 1, 2, and then the peace sign, 1, 2, peace sign, right? All I did was I just slid that down, and that's an easy way to attach and remove bonds to generate isomers or structural isomers of organic molecules. So that's isobutyl. Then we have, so I just do the exact same thing, but I slid it down 1 more. Right, so I took this and I slid it all the way to the first carbon there. So we go up here, 1, 2, 3, 4. We still have 4 carbons there. And if you counted all the hydrogens, we're not going to do that, but the number of hydrogens would be the same. This is sec-butyl. And then the last one is chicken feet. That's called Turk-butyl. Right, so all of these have the same number of carbons and same number of hydrogens. So they're all structural isomers of each other. And depending on how this group looks, you name it differently. Right, so if you saw this group attached to a third carbon, you would put 3-isobutyl pentane if it was attached to a pentane molecule. This would be 3-Turk-butyl pentane. I'm not going to be testing you too heavily on these. It's a lot to remember. But these are what these represent, right? The R, I want you to be familiar with the R notation to say this is an arbitrary parent chain. And these are isomers of the butyl alkyl group. All right. Any questions on that? I'm going to put the dots for each of the carbons here. 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Spelled alkyl up there wrong. All right, so that covers it for most of the alkanes, right? So we talked about one functional group for organic molecules. And you saw the list. It's a pretty long list of organic functional groups. But the naming rules, if you understand alkanes, is similar for a lot of the other compounds. So for unsaturated hydrocarbons, this means we have at least one double bond, or we could say we have at least 2 sp2 carbons, or 2 sp2 carbons, right? That would be a trigonal planar geometry for carbons. So the number, the only thing that changes for alkenes is you have a number and a dash to indicate what carbon the bond starts at. And then the prefix, this is the same for alkanes. And then the suffix becomes "-ine" instead of "-ane". So if we have something like this, right? What carbon does the bond start at? What do you guys think? How would you number this? What would put it on the lowest possible number? How would I?
Oh, then just one.
Yeah, you would play it. You could number this chain 1, 2, 3, right? Because now the highest priority group on the alkene is the double bond, right? So this has a higher priority than alkanes. So you're going to number this chain such that the alkene goes on the lowest possible number, right? So that's something to keep in mind for you. Put double bond on lowest number if it's the highest priority. So this would become 1, and then how many carbons are here? 3. Does anyone remember the prefix for 3? Prop, right? So this would be prop, and then -ine because of the double bond. Right, and all the other rules still apply. The only thing is that if we have an alkene and you have other alkyl groups on there, you're going to prioritize putting the alkene on the lowest possible number over the substituent groups of the alkyl or halogen in that case. Colin?
If you had a double bond, would you ever have a double bond and a triple bond?
Yeah, you can have a double bond. You can have something like,
Would you start with the triple bond?
I'm not going to give you guys that because those have weird, those become, so an alkyne is going to have a triple bond. So the prefix or the suffix is going to be ine for those. But if you have a mixture of functional groups, it becomes a alkanine, right? So you have the en from the ene and then the yne from the triple bond. And usually in those cases, the double bond has priority over the triple bond. But that's we're not going to worry about mixing them too much. You guys have plenty of practice that in the future. Right, so you could have something like this though, a triple bond and a double bond on the other side. Right, so all the other rules are still the same. So here we have 2-methyl, 2-pentene, right? How would we draw that? So how many carbons are in, so again, we're gonna start with the number of carbons in the parent chain. How many carbons are there?
Oh, wait, for the parent chain?
Yep, 5 carbons, right? So I'm gonna start with 1, 2, 3, 4, 5. Those are my 5 carbons. I have a double bond starting on which carbon?
2.
Yep, this is the location of the double bond. Right, so that starts, and I'm just gonna number this to make it easier for myself. That's my double bond there. It starts on carbon number 2. And then I also have what on 2? A methyl group, right? So this means that there's a methyl on carbon number 2. And methyl has how many carbons in it? 1, right? So that means that, I'm just going to erase this 2 here because it's in the way, that this is just going to go up like that, right? So this would be 2-methylpentene. And the idea with the naming, as annoying as it is you want to be able to write the structure from the name and give a name to a structure so people can read it and they understand what structure you're talking about. So really this is like a map to drawing the structure is how I think of it. And so it should have some sort of logic and sense to it. Double bond. All right, any questions on alkenes?
For the pentene, can we draw the double line from 1 to 2, or does it have to be?
The number of the double bond is always where the double bond starts, going in order of the chain, right? Because we're starting from this side, going that direction, it starts at carbon 2 and goes to 3. If it was starting here, that would be 1 pentene, right? Because it's always the double bond is, the number indicates where the double bond starts. And also, a side note, for example, if you had a cyclic molecule, you can have something like double bonds that are in cyclic molecules like benzene we saw earlier. And the only difference between this is that you'd put the double bond on carbon 1, 2, 3, 4, 5, 6. This would be 1 now cyclopentene. And if you have a structure like this where there's only 1 double bond in there, a lot of the times, especially for cyclic molecules, they won't write the number 1. It's technically more correct to write it, but because you can number the cyclic molecules in any way you want to, you're always going to put it on the number 1 carbon here. So that's why usually you'll see people just write this as cyclopentene. If you have multiple double bonds, you put them in the lowest possible order, and then it becomes pentadiene. So you put a prefix at the end. So if you have something like this, we would number this 1, 2, 3, 4, 5. This is 1, 3 pentadiene. I'm not going to give you guys any dienes, but this is just for when you see this in the future. You have a di because it's indicating that there's two double bonds. Right, and you can have that in the cyclic form too. So you can have that, 1, 2, 3, 4. That would also be 1, 3, cyclo, penta, di, ene. Like I said, I'm not going to give you any dienes, but this is just so you're exposed to it. Okay, any questions on that? What about alkynes? What do you guys think is going to happen for alkynes? If you had to guess based off of our trend. So alkanes, the suffix was ane. Alkenes, the suffix was ene. Alkynes, the suffix is ine, right? So it should be ine. So alkynes, same as alkenes, but suffix is replaced with ine. And usually when you have an alkyne in a carbon skeleton, they don't draw a kink in the line. It's drawn this way. Because the sp, hybridized carbon, forces the structure to be linear at that point. Right? So it can be sometimes hard to look and interpret the alkynes. But really this alkyne is going to have 1, 2, 3 carbons here. Right? In between the 1, 2, and 3 carbon, there's going to be a triple bond, meaning it's a linear part of the molecule. All right, we have 2 unhybridized p orbitals in both of those sp hybridized carbons. So those overlap and form 2 pi bonds. Carbon number 1 has how many bonds drawn to it right now? Yeah. 3, right? So how many hydrogens are attached to that are implied there? 1, right? So there's technically a hydrogen right here, right? Because it's a linear, this carbon is linear, right? So there's a hydrogen drawn, that's not drawn there. So we're always keeping in track there. What about to carbon 2? How many bonds are attached to carbon 2? 4. So how many hydrogens are there? 0, right? So whenever we have an sp carbon in the middle of a chain, it's always going to have 0 hydrogens attached to it. And then here we have an sp3 carbon, right? 4 bonds attached to it. How many bonds are shown? 1. So how many hydrogens should there be? 3, right? So 3 hydrogens should be bonded to that one. All right. So take a second and see if you can draw 3 isopropyl 4 methyl 1 pentyne. I can tell you that these are very tame compared to next semester's. I've seen those exams, even though I just was subbing for the lab. I've seen the names in those exams. Because right now we're just looking at naming substituent groups. You can do things like specify the stereochemistry, which isomer you have in terms of chirality, optical isomers, if it's cis or trans, all of those things. Let's see, do I have a section on naming? All right, how many carbons are in the parent chain here? 5, right? Pent means there's 5 carbons in the parent chain. Ine means, what does ine mean? There's a triple bond. and 1 tells us that that's where the triple bond is located, right? So our parent chain, I'm going to draw my 5 carbons for the parent chain. Technically, for a triple bond, we usually draw it linear, but if you were to draw it like this, that's okay, right? That says there's a triple bond between, I'll just draw you. We have 1, 2, 3, 4, 5. This highest priority group is a triple bond. We're putting on the lowest possible number here. Then we have on the 3rd carbon, we have what group there? Isopropyl. And what did isopropyl look like? Everyone show me with their hands what isopropyl looks like. Yeah, right. That's it. So isopropyl on the 3rd carbon. And then on the 4th carbon, we have a methyl group. And methyl is how many carbons? 1, right? So that's just going to go up like this. Question?
For the first triple bond, is it usually more straight or does it not?
Yeah, I said if you draw it like this, it's okay right now, but generally how this will be drawn, it'll be drawn like, and you might even see it drawn like 2, so 1, 2, 3, 4, 5, like this, right? And the fact that there's a triple line right here just implies that 1, 2, 3, 4, 5 carbons. It's a little harder to see, that's why I don't draw it like that. Usually I intentionally put a break right here, so at least it looks something like this. I'll draw it, even if it's straight, I'll draw it like that, so that it's clear that there's the same number of carbons. 1, 2, 3, 4, 5. But yeah, usually that forces that part of the molecule to be linear, right? Again, this is why carbon is important. It based off the hybridization of the carbon, it restricts the geometry of the molecule. So it can have something very highly flexible with sp3 carbons or very highly rigid with sp carbons. All right. And so this leads us just into a discussion that we talked about last time, which is organic isomerism, right? So we've talked a little bit with the substituent groups, how propyl can have different isomers, different connectivity, right? Structural isomers were same chemical formula, and different connectivity, right? So they're connected to each other in different ways, but have the same number of each type of atom. So for example, when we look at propane, we'll say here we have 4 carbons, right? So this would be butane. We can move one of the edges like that, and now that becomes 2-methyl propane, but those are isomers of each other. If those attach to an R group, we would say it goes from propyl to isopropyl, right? But if it's just a standalone molecule, we have to name it using the convention. So that's butane and 2-methyl propane. Those are isomers of each other, same chemical formula, but different connectivity. We can have more complicated ones. For example, if we have C6H12, what would the prefix be for a molecule? Or if you had to guess a prefix for that molecule? 6 carbons, so there'd be hex, right? If we did this molecule here, this would have 6 carbons, and each carbon has 2 hydrogens bonded to it because it's already had, each carbon is shown drawn to bonds. So it'd be C6H12. This is an isomer with, so let me draw it a little bit better, a structural isomer with 1, 2, 3, 4, 5, 6, with a double bond existing inside a chain. If you count the number of carbons and hydrogens here, those will have the same amount. All right, so that's 1, 2, 3, 4, 5, 6 carbons, and then we only have 1 carbon in each side of the double bond, or 1 hydrogen on each side of the double bond. Those are both structural isomers. Different, same chemical formula, different connectivity. Stereoisomers are going to have the same connectivity, same chemical formula, but different spatial 3D arrangement. So same connectivity, same chemical formula, but different spatial 3D arrangement. Or different spatial arrangement. So geometric isomers were the different spatial arrangements. Those are like cis and trans isomers. We use those for describing double bonds. So if we have something like this versus something like that, the groups go on opposite sides of the double bond. So this would be trans, and this is a cis isomer. You can also specify the isomer in the name. For example, there's 4 carbons in both of these. The one on the left, let me put double bonds a little farther over. This would be cis 2 butane, and this would be trans 2 butane. I'm not going to ask you guys to name these, but this is, if you see that, that's what that is. You can also have what are called E and Z isomers, where it's not just simple chains going cis or trans to the double bond, but if you have multiple things like something like alcohol groups, so if there's an OH coming out here and an OH coming out here, or if the OH groups, right, there's multiple groups that you have to analyze here. This would be E and this would be Z. I'm not going to test you guys at all, I'm just, you'll see that next semester, right? Because it's priority groups, there's multiple groups that you have to analyze in that case. Those are geometric isomers, and then you have optical isomers, and these are chiral mirror images of each other. So let's say we had 2 tetrahedral molecules, and they were perfect mirror images of each other, right? So let's say each of these represent a different group. For chirality, you need different groups at each position on each molecule. So this is molecule A, and that's molecule B. See how they're mirror images of each other? It looks like one's looking to the mirror. If you try to rotate these in any way to be superimposed on each other, you could not. So you will never be able, it's like your left and right hand. Right? This is the best example of chirality. If you take your left and right hand, right, they're mirror images of each other, right? It's like this, your left hand looking in the mirror, right? But if you try and superimpose your hands on each other, right, this is not a superimposition, because now the back of my hand is facing you, where this is the front of my hand facing you. This is the same thing, it's a mirror image. There's no way you could rotate or do any operation of symmetry, is what we call it. Rotate, reflect, invert, do anything like that to get your hands to stay on top of each other. And those are what are called optical isomers, and it gives rise to chirality in molecules. Chirality is important. So for example, one of the burning questions in research is, why are all proteins naturally found in the L isomer, right? Or the L chiral conformation. And they're called optical, again, just because that's how they rotate light when it interacts with them. All right, so it's related to how these molecules interact with light. Again, I'm not really going to ask you to look at chirality, but when you do go into organic chemistry, you'll have to look at a molecule and identify the chiral centers, right? Where are the chiral centers? Because that's how it's going to be involved in how you name the molecule. That's going to be involved in certain things when you're taking measurements of the molecule. All right, any questions on the isomerization of organic molecules? For the most part, same as what we talked about already, just to review. Cis and trans are all you focus on with the geometric isomers in organic compounds. It's because we don't have complicated shapes like square planar, octahedral, and stuff. All right. Okay, so then there are some simple chemical reactions right? So a big part of organic chemistry is understanding the products of reactions. So you kind of feel like you're doing a lot of chemistry. Chem 1B is a lot of math, understanding the energy movement, equilibrium, kinetics, all of these things. In organic chemistry, you're kind of moving back to looking at specific reactions. Can I predict the product of a reaction? So some basic reactions are halogenation of alkanes. So if you have methane, which is just a carbon with 4 hydrogens, and you react it with chlorine gas, you will eventually replace all of the hydrogens with chlorine, right? So this is a spontaneous reaction for chlorine with hydrogen. However, this happens stepwise, right? It takes a while. It depends on how long you bubble chlorine. Depends which product you get, right? So you'll get this, you'll get a little bit of H2 chlorines, you'll get a little bit of 3 chlorines and 1 hydrogen, and you could potentially also just get only 1 chlorine and the rest hydrogen. It happens stepwise, so it just depends on how long you bubble the chlorine gas. The specific mechanism you probably won't get into until the end of organic chemistry. It's a radical reaction, so usually this requires a little bit of light for this to happen. Creates a radical species that's very reactive. Right, whenever you see something over the reaction arrow, that just means those are the reaction conditions. So light, heat, catalyst, those are things that are going to be common in organic chemistry. So if you had, for example, a propane, you bubble chlorine gas with light over it, eventually you will get halogenated propane. Right, and a lot of organic chemistry is, can you predict the products based off of the reaction conditions? And then, so those are with alkanes. Alkanes, you don't study a lot of reactions with them. Alkenes, you do though. Alkenes are a lot more reactive because of the pi system. It makes them much more reactive species. So the common ones you'll see are hydrogenation and halogenation of alkenes, right? So alkenes are your double bond. If you have something like propene here, you bubble chlorine gas over it, or hydrogen gas, the 2 potential products that you'll get. You get rid of, these are elimination reactions is what they're called, because you eliminate the double bond and you replace it with 2 hydrogens in that case, right? You replace it with 2 hydrogens where the double bond was. If you halogenate the reaction, you replace the double bond with the 2 halogens that you have. Eventually you will halogenate all of it. However, if you use hydrochloric acid instead of chlorine gas, right, you can use HCl, that'll hydrohalogenate it as well. So there's halogenation, hydrogenation, and hydrohalogenation. So this can also go, if we have something like this plus HCl, this will put the chlorine on the, let's say the more substituted carbon because it's bonded to more of the carbons, and then the hydrogen goes on the less substituted spot. You can also have dehydration of alkenes or alkynes. So any reaction you see for alkenes also work for alkynes. They just have 2 pi systems, so it can be to a higher degree, the reaction happens. The hydration, if you think about hydration, what do you guys think of when you think of hydration? If someone says you need to get hydrated, what do you? They need to drink water, right? So what we're doing with hydration is we're adding water to the molecule. We're not going to add exactly a water molecule because that's already a full valence. But we're going to add one hydrogen and one OH group. We're going to add an alcohol and an OH. And so this requires usually acidic conditions. So H2SO4, or sometimes people will just put H plus to indicate acidic conditions, and needs to be in the presence of water. And you get an OH group and a hydrogen. And usually the alcohol is going to go, so this is called an alcohol group. The alcohol group, it goes on the less substituted carbon. And what we'll talk about, this is the lower degree carbon. And all that means is the degree of the carbon just tells you how many other carbons that's bonded to, right? So it goes on this creates a primary alcohol because it goes on a 1 degree carbon because that carbon is only bonded to one other carbon atom. And you guys will learn different conditions that'll learn to to make your different structural isomer here, right? So you can imagine that, well, sometimes the OH group might go on the other carbon, but that requires different reaction conditions, right? So the reaction conditions determine the specific product that you'll get. So a lot of organic chemistry is going to be, okay, you have it in these conditions, you know where to put the alcohol group, but if we change the conditions, do you remember that now the alcohol group goes on the other side? And that's because the reaction mechanism is different. It attacks, there's attack of the different carbons by whatever solvent molecules you have. Where does that attack happen? And that determines where your final product is going to end up, or where the alcohol group in this case is going to end up. So those are the only reactions. There's 4 simple reactions for the alkenes and alkanes. So you have halogenation of an alkane, hydrogenation and halogenation and hydrohalogenation of an alkene, and then hydration, which is the addition of water molecules or creating an alcohol from an alkene. Right, and so this is usually where first semester OChem ends, right? At this point, okay, you've talked about alkenes, alkynes, structure, hybridization, isomerization, and then mixed into all of this, you have spectroscopy that's added. Spectroscopy is NMR, IR spectra, looking at what lab experiments can you actually do to test what structure molecule you have. And so for the purpose of the final and stuff, you'd probably just be asked to make some simple products, right? You're given these reaction conditions. Here I have propene, but if it was pentene, could you predict what the product would be in the condition of water and in acid? All right. And so these are mostly just hydrocarbons. We introduced the making of an alcohol just now. But these are the simple hydrocarbons, right? These are just reactions of compounds that just have hydrogen and carbon. Organic chemistry extends to not just those, but all of these different functional groups. We have alcohols, ethers, aldehydes, ketones, carboxylic acids, esters, and amines. Esters are the smelly ones that we're going to do on Tuesday. So there's a large array, and this isn't even all the functional groups, right? There's probably 20 other functional groups that are more specific than these ones. Alcohols, all right, so I use the notation R is like the main chain, and alcohol just looks like an R group bonded to an OH. That's how we define an alcohol. So now when someone says isopropyl alcohol, that you use to clean something up, now you know that that is just an isopropyl with an alcohol attached to it. So IPA, isopropyl alcohol, not IRA. I think that's a group in Ireland. IPA just looks like that. That's what isopropyl alcohol is that people use to sterilize and clean stuff is. I drew it a little bad. That's what IPA is. Ethers are when we have two R groups that are separated by an oxygen. So you have an oxygen in the middle of a chain. So an ether is going to look like this. And you put R prime, just indicates that can be any other chains. The two chains don't have to be the same. For example, you can have an ethyl on one side and a propyl on the other side. And actually that's how you name ethers. You just do ethyl, propyl, ether is how you would name that. An aldehyde has a functional group called a carbonyl group. An aldehyde is going to be an R bonded to a carbon that's bonded to a hydrogen and double bonded to an oxygen, right? This specific group right here is called a carbonyl when you have a double bonded oxygen to a carbon atom. And aldehydes, ketones, carboxylic acid, esters, and amides are all going to have this motif, is what we would say. This element is going to be in these functional groups. So you notice that this carbon is double bonded to, how many bonds are drawn to that carbon right there? In the center, this one right here. How many bonds are drawn to this carbon? 4, right? So can this form any bonds with anything else? So where do you think aldehydes are going to be located on organic molecules? Aldehydes are only going to be located at the edge of the molecule, right? So you'll never see an aldehyde that's attached inside of a ring. So this is always going to be, right? This would be propanal is how we name this. It's always going to be the aldehyde functional group is at the edge of the molecule. It's a terminal functional group because the carbon there is already taken up all of its bonding spots. Ketones are similar to aldehydes, except we lose the hydrogen and that's just bonded to another R group. So ketone is going to be an R group, double bonded carbonyl, and then another R group on the other side. Right, so an example of that. What would the two R groups be in the molecule that I just drawn? How many carbons are in each R group there? There's 2 carbons total. How many carbons are total in that molecule? 3, right? So this carbon, that's our carbonyl carbon, right? That one's that one right there. So the red ones represent our R groups. And how many carbons are each in each of the R groups? 1 in each, right? And what's the prefix for 1? Meth, right? So these would be 2 methyl groups attached to a ketone or a carbonyl. And then this molecule is called a ketone. So that molecule, that's called acetone. Does that acetone sound familiar to anyone? What do you use acetone for? To remove paint and nail polish, right? The acetone is a good solvent for these reasons. But acetone, right? The 2 R groups are just the methyl groups. It's a very simple ketone. You can have very complicated ketones, you know, something like this. These molecules can get tougher and tougher to name and identify. But that's also a ketone. Those are examples of ketones. The R groups are just different for them. Carboxylic acids are also going to be another terminal group. And what do you think a physical or chemical property of carboxylic acids will be? What do you think happens if you put carboxylic acid in water to the solution? Carboxylic acids are, what I'm getting at is they're acidic, Right, so carboxylic acids are acidic. That proton on the carbonyl, right? So we have our carbonyl carbon here, double bonded to the O, and instead of a hydrogen, like in an aldehyde, we have an OH group. This proton is a very acidic proton, and that can be donated to make H3O plus in water. So these, for example, we can have something that looks like this, CH3, COOH. And what's the acid I keep telling you guys about? Acetic acid, right? So this is acetic acid. That's the acid in vinegar. It's a carboxylic acid functional group, right? And our R group is what in this case? CH3. So it's another methyl R group. So really the IUPAC name isn't acetic acid. That's the common name for it. And some common names are used interchangeably. But this is methyl carboxylic acid is another name for that. Esters are a combination of a ketone and an ether, and they're broken up into a carboxylic acid side and an alcohol side. And the reason they're defined that way, right? So this is a carboxylic acid side right here, and this is the alcohol side of the molecule, because to synthesize esters, you use an alcohol, you use a carboxylic acid, and heat or acidic conditions, right? So either an acid or base works to make these two. And so it's a type of condensation reaction. That's the one we're going to do on Tuesday. And so you have two R groups that are separated by the ester functional group, right? And it looks like a mixture of the ether and an aldehyde, and a ketone, right? So it's a carbonyl and an ether right next to each other. And then amines, we can have amine itself in R group, H, R prime, H, this, and then the last one is R double prime, R prime, R, like that. We can have a number of different types of amines. Amines just have a nitrogen group there, and the degree of the amine is just determined by the number of carbon groups that are bonded to this. Right, so this is a tertiary amine. This is, we don't even classify that amine. This is a primary amine, and this is a secondary amine. And so the classification that's kind of confusing is amines and alcohols. Alcohol is classified based off of the carbon that it's bonded to. Amines are classified by the number of carbons that are bonded to the nitrogen. And so let's see, what do I want to go over? Okay, so we'll finish off with alcohols just because those are an important one and how to classify them. And then we'll end the lecture there for today. The other ones, the other functional groups aren't as important, but the reactions we'll talk more about on Tuesday when we're doing the lab for that. Okay. So for alcohols, again, this is the function group ROH, right? Naming alcohols is the same as naming an alkene. Naming. Alkene, except the prefix ENE is replaced with OL. right? So if we have an alkane, like methane, which is just one carbon, this becomes methanol, right? So methane looks like a carbon with four hydrogens. Methanol just has an alcohol group attached to the carbon atom. If we look at something a little bit more complicated, let's say we have pentane, right? 1, 2, 3, 4, 5. And now we go to 1, 2, 3, 4, 5. OH. The same way that we name an alkene by indicating where the double bond is, now we number the chain according to put the alcohol group on the lowest possible carbon. There's no double bonds within the chain, so this becomes 2 pent and all, right? Because the 2 tells us that on the second carbon, 1, 2, 3, 4, 5, there is an alcohol group. And alcohols have a greater priority than alkanes, alkenes, and alkynes. Right, so for our purpose, alcohol will be the highest priority group that we look at. And so alcohols are classified the same way amines. I said you have primary, secondary, tertiary amine. Alcohols are classified, but they're classified not by the number of carbons that are bonded to it. They're classified by the carbon that they're bonded to. And it's related to the degree of the carbon, which is just the number of carbons that the carbon of interest is bonded to. Right, so if we have, let's do a really big molecule. Something like this. This carbon is bonded to how many other carbons? 1, right? So this is considered a 1 degree carbon. This carbon is bonded to how many other carbons? 2. So this is considered a 2nd degree carbon. And this carbon is bonded to how many other carbons? 4. 1, 2, 3, 4, right? I forgot to draw the 3rd degree carbon. This is a 4 degree,
Would it technically only be able to go to 3 degree?
Alcohol will only be able to go up to tertiary. The carbon can go up to 4, but the alcohol, because if alcohol is going to take one of the binding spots, so I'll talk about that on the next one. But yeah, that's a good point, right? So that's a 4th degree carbon, and then the one that I just highlighted is right here. What degree is that one? 3rd degree carbon. Right, so the degree of the carbon is just based off of the number of carbons it's bonded to. the classification of the alcohol is dependent on the degree of the carbon that it's bonded to. So I'm going to copy and paste this and bring it to the next. So copy. All right. Let me know. Am I good to go on to the next slide here? Yeah. So the alcohol right can only go up to, so we'll use, what color? We'll use black to signify the OH. Now we put a alcohol group on all these carbons, but we can't put an alcohol group on the 4th degree carbon. Why not? How many bonds can carbon form? And the 4th degree carbon already has all 4 bonds taken, so we would have to break one of those bonds to form it, right? So there's no such thing as a 4th degree alcohol. So 1 degree carbon, this is called a primary alcohol. When a 1 degree carbon, when an alcohol is bonded to a 1 degree carbon. A secondary alcohol is when a alcohol is bonded to a 2nd degree carbon. And a tertiary alcohol is when a alcohol group is bonded to a 3rd degree carbon, right? So amines, it was how many groups, R groups, are bonded to the amine that determines if it's primary, secondary, or tertiary. For alcohols, it's how many or what degree carbon is the alcohol bonded to. So it's dependent on the R group that it's bonded to, whereas amines are how many R groups are bonded to it itself. All right, any questions on alcohols? So the reason that the degree of the alcohol or the classification of the alcohol is important is because for certain oxidation and reduction reactions, you can always oxidize an alcohol depending on the degree of it. So for example, tertiary alcohols don't oxidize, secondary and primary alcohols do oxidize to aldehydes and carboxylic acids. Secondary alcohols oxidize to ketones, and 3rd degree, there's no reaction when you oxidize those. But we'll talk more about the reactions, either if you start working on the worksheet right now, or on Tuesday when we go over it in lecture, going over all the work, right? So we've kind of covered the base of all the different functional groups. I'm gonna post the completed notes for this on Canvas, and on Tuesday we'll go over working through all of the different types of problems, because we could go through all the different, reduction, oxidation of alcohols, naming convention of aldehydes and everything. But the naming conventions don't really change a whole lot, and you can see it in the notes. It's easier to kind of get practice doing that. All right, so we'll end there for